Yes, sir. That yes, sir. I'm trying to figure it out, sir. Yes, announce. Yes, sir. Okay, sir. Uh, some problems. There is some problems with audio, and sir has requested me to read this. Yes, sir. Okay. Uh, okay, sir. So, some problem with audio in MS Team now. Through Nikhil Mobile, we are trying to give my voice. We appreciate Nikhil for this attempt. Okay. So, yes. So this is the laid out program for the remaining theory course, and on 11th Feb we are having assignment submissions, and 12th we have PPT presentation of at least 3 to 4 students per day. Okay, sir. And last class will be on 12th March, as decided in Senate. Sir, but assignment submission was supposed to be on 15th. Okay, sir. Um, uh, Jayanthu sir has instructed that means we need to give some progress for the assignment from 11th, but the final submission will be on 15th only. Those who have prepared their PPTs, they can volunteer for the presentation for tomorrow. Those who have completed must come forward. This is the CP2 question. Caving height with 6 meter height of extraction. What is caving height in other similar geomining situation? Okay, sir. So I need to read the full slide, sir. Okay, sir. Following approaches are generally used for estimation of the support requirement for long wall panels. The support requirement based on these approaches, along with the adequacy of the support in a typical panel, is as follows: Berry's approach, Sigurt's approach, Siska's approach, Das approach, Joysons approach, and Gupta's approach. We have discussed these things in the last lecture, and this is the uh, so CP1 question is: go for support requirements in repealing panel. How much more you expect in long wall panels? So, if anyone is interested to answer the CP question, they can respond now. Uh, Anybody for the CP answer?
Sir, CP2 answer is 100 when we take bulking factor 1.06.
Yes, sir. About this DAS approach, sir. Uh, uh, Please tell your name too.
Rohit Kumar.
Rohit Kumar has answered, sir. Rohit, answer the question.
Sir, CP2 answer is when we take bulking factor 1.06, the answer we get is 100 meters. Sir.
Anybody interested to answer CEP1? Uh, Okay, sir. This is what was shown in the last class. Das approach. So today we are going to discuss about Das approach. This approach is based on Indian longwall mining experiences, where caving is predominantly parting plane controlled. The capacity of the powered support in ton is estimated as Das is Ty equals to R into SF upon. Okay, okay. So in the given equation, R is resistance to be offered by the powered support in turns. SF is frequency of factor of safety, which is 1.5 in the case of medium strength to stronger massive sandstone, and 1.2 in all other cases. And neta I is efficiency factor for the powered support due to inclination of legs, which is 0.85 for choke seal support and zero point 0.8 for seal supports. And one is efficiency factor of the powered support due to leakage in the pipelines or valve system and mechanical defects, which is 0.9. Okay. Okay. In the given equation, W1, W2, W3 are the weight of first, second, and third roof layers. H1, H2, S3 are the thickness of first, second, and third roof layers. So L1 is distance between long wall face and caving edge. So 90 degree minus alpha 1, 90 degree minus alpha 2, 90 degree minus alpha 3 are the caving angles of the first, second, and third roof layers. P is the distance from the centroid of resistance offered by the powered support, which is 3.78 meters. Based on different sections of strata, as given in borehole logs, the following sequence of roof layers were considered for estimation of the support requirement for the above approach. So we are going to discuss some case. Case 1 is coal is 0.9 meters, shale 0.3 meters, sandstone 58.3 meters, and so case 2 is coal 1.2 meter, in which 0.9 meter is coal and 0.3 meter is shale, sandstone 4 meters, and sandstone again 5.9 meter. And similarly, there may be different cases which can be considered depending on the layers. And this is the way how it was calculated using different values from the marks. The capacity of power supports in turns for the above case are given in the following table. So this is the overhang, and there are the different cases for the overhang. And based on the above approach, the minimum support capacity required is 2331 ton. Okay. In the cases second, third, fourth, and fifth, we required lot of supports, but it is not now practicable to provide that much support. Now only we can provide support up to 12,000 tons. 1200, sorry, 1200 maximum. And so so this shows the limitations of different approaches. So we are moving on to next approach, that is Joyson's approach. So Joyson found the relationship correlating convergence at a face with load bearing capacity of the powered supports, and in the given equation CV is average convergence, which is mm per meter of phase advance. A is subsidence factor for caving is 1. D is depth of mine, which is given by m equals to 180 meter. H is extraction height, which is 4.5 meter. R is load bearing capacity of the support, which is given by T per meter of the face. That is T is ton. It seems it seems that its application is again limited to convergence value exceeding 55 mm per meter, as undesirable negative values would be associated with R if CV is less than 55 mm per meter. As per the above equation, with CV equals to 60 mm per meter, the support capacity required would be 1142 ton per meter of the face. This is equivalent to the required load bearing capacity of about 1713 tons per silt. As per this approach also, even for a height of extraction of 3 meters, the support capacity should be more than 900 ton per silt, with a safety factor of 1.5 for better strata control. Obviously, the capacities required would be still higher in case of greater extraction thickness. So this is the approach in developed by the Indian investigator. So this is Gupta's approach. For better face condition, the leg closures should be within 3 mm per meter of face advance. And these are the paper citations. Uh, and the mean load density MLD should have been as follows for uh, uh, so this is the Kotadi mine data, which was explained earlier by Jayanthu sir. And move, which is so this has got. So what were the professor names, sir? Professor. Okay, sir. So this has got some international arbitrations, and Professor, which is explained by Professor S.S. Peng and Professor Fairhurst, Fairhurst through CDF France, and from Indian counterpart, Professor Jayanthu sir and R.N. Guptas. Okay, sir. So in the given equation, C is phase convergence, which should be less than 3 mm per meter for face advance to achieve code roof and face conditions. K is a constant, which is 40 for competent roof, 150 for easily caving roofs. M is extraction height, which is given in meter. MSLD is mean setting load density, which is given as ton per meter square. MLD minus MSLD is equal to 0.224 plus 0.438 MSLD. For K equals to 100, MSLD is 91.36 ton per meter square. And mean support density, which is MLD, is 131 ton meter per square. Sorry, ton per meter square. As per this approach, the mean load support density should be more than 130 ton per meter square for better strata control. And 130 ton per meter square appears to be reasonable. So, and so we can utilize it for any longwall face condition in Indian mines. And we are now moving on to longwall investigation case study in Indian mines. At VK7 incline, extraction of